Today's lesson is a continuation on chapter 3.4, ratio of volumes of similar solids. We'll start with example 18. Now you are given the ratio of the base areas of two similar solid copper cylinders is 9:16. Take note that this is the ratio of areas, which you must know it is simply the square of the ratio of sides. Okay, so now find the ratio of the radii, so referring to the sides or the base of the cylinders. So now that you are given this is equals to 9:16, they are asking you for the ratio of sides. So how do we go backwards? We need to square root it. Okay, so I don't quite like the presentation over here. This is what I will do. Ratio, okay. Area, big, divided by area, small. Okay, how about small one first, huh? Because they started with 9, then 16. So the small one over the area of the big one is equals to 9/16. So then, ratio of the radii, radius, small over radius, big, must be equals to square root of 9/16, which is 3/4. So ratio is 3:4. I prefer to work with fractions rather than to work with ratio over here. Okay, so moving on, part B. They now want the ratio of the volumes of the cylinder. Okay, ratio of volumes, we know that it is going to be the cube of the ratio of sides. This means that my volume big divided by volume small. Oh no, I keep writing it wrongly. They wanted the small one first. Small over the volume of the big one. It's actually equals to 3/4, which is the ratio of sides, and we cube it. So we get 27/64. So the part B, ratio equals to 27/64. Now think about it. If the question did not ask you to do part A, okay, so we didn't have this, are you able to do part B? Given that they want the ratio of volume, but they only give you the ratio of area. So typically, this is what would happen for your exams and your tests. We will not tell you explicitly to find the ratio of the sides. So we expect you to be able to go from area, the ratio of area, to the ratio of volume. You are expected to know that you have to find the ratio of sides as an intermediate step before you can move on to find the ratio of the volume. Alright? So next part C. They tell you the mass of the smaller cylinder is 540 grams, and to find the mass of the larger cylinder. This topic is on ratio of volumes of similar solids. We have not taught you ratio of mass of similar solid. So then how do we do this question? First, let's try to think about it. If the mass of the smaller cylinder is 540 grams, do we expect the mass of the larger cylinder to be greater? Yes, we should, because they're both made up of the same material, which is copper. We also learned in physics that density equals to mass over volume. And for copper, the density is fixed. In fact, in our syllabus, regardless of the material used, the density will be fixed. If they tell you that two similar solids are made of plastic, but then these two plastics, they will tell you that it is the same type of plastic. So the densities of these two figures will be the same. It could be plastic, it could be glass, wood, whatever it is. Just note that the density will be the same. So what does this therefore tell us? If this is fixed, and if the mass increases, the volume must also increase. If the mass goes down, the volume must also go down for it to be fixed. Another way of looking at it is, if we multiply we will get mass equals to density times volume. Okay, and density in this case is fixed. So we say that mass is proportional to volume. So we can actually write mass equals to kV. But in physics, we actually write K as rho. Okay, mass equals to rho V. In mathematics, since we always use K as a constant, we say mass is proportional volume. This is what we write. M equals to K times of V. As the volume increases, our mass will also increase proportionally. As volume decreases, mass will also decrease proportionately. Okay, so these are some ways that we can write it. This leads us to the conclusion that ratio of mass is actually equal to the ratio of volume. Okay, so you should be wondering, how do we get this relationship? Let us use this formula. Density equals to mass divided by volume. For the larger object, okay, for the larger cylinder, mass big divided by volume big must be equals to the density, right? Then at the same time, we also have mass small divided by volume small must also be equal to the density. Since these two are made of the same materials, the densities must be the same. These two are equal, which also means that these two ratios are now equal. Mass of the big cylinder over the volume of big cylinder is equals to mass of small cylinder over volume of small cylinder. Okay, we still have not arrived at this yet. Ratio of mass equals to ratio of volume. Because on the left hand side over here, I've got ratio of mass divided to the volume. On the right side is the ratio of mass to volume. I want ratio of mass versus ratio of volume. So let's see how we can manipulate this. If I choose to multiply like this, I will arrive at mass big times volume small equals to mass small times volume big. Then now, since I want ratio of mass, I will divide both sides by the big mass. Okay, so dividing by mass big, here likewise divide by mass big, will result in volume small equals to mass small divided by mass big times volume big. Okay, so now I want to divide both sides by volume big. So I'll just divide both sides by volume big. So this will give me volume big, and this one disappears. So what we have over here is that ratio of volume, small one over the big volume, is actually equals to the small mass over the big mass. This is the conclusion that I am trying to get you to see. And all this happen because they have the same density. I encourage you to know how this is derived. Okay? Otherwise, you can simply quote this relationship. The mass of the smaller cylinder divided by the mass over of the larger cylinder is actually the same as the volume of the small cylinder over the volume of the large cylinder. Okay, that's rather intuitive. So now all we need to do is to substitute in values. They told us that the mass of the smaller cylinder is 540. So just put it in the numerator. The unknown is the mass of the larger cylinder, and we write down the ratio of the volume. So here we have the mass of the larger cylinder is simply 1280. So instead of writing it like this, like I told you, we prefer to write the unknown in the top left hand corner. So what do I always mean by this top left hand corner? This is my unknown. So mass big, this is how I write it, divided by mass small must be equals to volume big divided by volume small. And now I'll substitute mass big divided by the mass small, which is 540, equals to the volume of the big one, which is 64 divided by 27. So mass big is simply 64 over 27 times 540, and you get the same answer, 1280 grams. So please take about 10 minutes to do try it 18. Once you get our answer, please check with the back of the textbook. If it is different, check with your partner. Next example is 19. Here we have an inverted cone, and this is a very popular question because you may not really see where are the two similar solids. Okay, so let's understand what this is. Here we have an inverted cone that is upside down. It has a height 18 cm. This refers to the vertical height, or the perpendicular height. It contains water whose volume is 8 over 27 of the capacity of the cone. So here they are trying to tell you ratio of volume. Find the depth of the water. Okay, so here this part is filled with water, and the volume is 8 out of 27. So in other words, if total volume equals to 27 cubic units, then volume of water is equals to 8 cubic units. And we say I used cubic units instead of cubic centimeters because 27 is not the actual volume, it's not the actual capacity. 27 and 8, they are just ratios. Okay, so without actually calculating the actual volume, we can use this to represent the ratio of volumes. Okay, so now the water that is inside the inverted cone has a particular shape. You should be able to see that it is actually an inverted cone as well. This part over here, inverted cone. And you should be able to see also that it is similar to the container in shape. Okay, they do not tell you that. You are supposed to be able to realize that. So here are our two similar solids, so two similar figures. Then they want us to find the depth of the water. So meaning this part. How much is this? We're going to use our relationship, that is volume big. No, they want us to find the, what do they want us to find? The depth of the water, which is the small one, right? So volume small over volume big equals to height small over height big NV cubic. So like I said, I like to put the unknown on the top left hand corner. So I should actually rewrite this to become height small over height big Ni cubic. This should give me the volume small divided by the volume big. I used height. You can use depth if you want to. So it's time to do some substitution. Height small divided by the height of the big one, which is 18. If I were to cube this should give me the ratio of volume, the small to the big one. So which is, according to the question, 8 divided by 27. So height small will be equals to the cube root of 8 over 27 multiplied by 18, giving me 2 over 3 times 18, which is 12 cm. So this is the depth of the water for part A. Now they want additional volume of water required to fill the cone completely if there is already 100 pi cubic centimeters. So this volume is 100 pi cubic centimeters. How much should this be? So they are trying to find the volume of the green part. What we do know is that ratio of volume for the small pyramid to the total container is 8 to 27. Okay. So this is what we can write for part C. If I know the total capacity of the container, then I subtract the amount of water that is currently inside, I will be able to find the empty space. Okay, so our goal now is to find the volume of the big one. So volume big divided by volume small is supposed to be equals to 27 over 8. So volume big equals to 27 over 8 times the volume of the small one, which is 100 pi, to give us 337.5 pi cubic centimeters. And all you have to do next is to find the additional water required by subtracting. (337.5 pi minus 100 pi to give us 237.5 pi. Get a value in 5 SF, round it off to 3 SF. So the remaining period, please do try 19. And these are the homework questions. that are due on Tuesday. So this is due 26th Feb. Now one more thing, before I forget, we know the relationship between ratio of volume and ratio of mass. So this is what we have. Ratio of volume equals to the ratio of mass. Now the other thing I need to know is, what about ratio of cost? Sometimes they will, for example, this copper cylinder question, how much does it cost for the material for the copper? They are going to be selling you the copper based on the mass of the copper and nothing else. So our next conclusion will be that this is also equals to the ratio of cost. Okay, this is with the assumption that cost is for material only. Okay, so this is for 3D figures. We can have questions on printing, for example, or painting. In that case, printing and painting, because it is two-dimensional, the ratio of cost will be equals to the ratio of area. Okay, so these are some of the variations that you may see.